Hello again. In this video lecture 9.2, we're going to be discussing the material in Chapter 9, Section 2 of our book. That section is titled Newton's Second Law for a System of Particles. But probably what it really is about, this section in Chapter 9, is what my key idea states. This section is really about determining how the center of mass of a system of particles is going to move. So let's remind ourselves about the previous video lecture, 9.1. There, I motivated why this special point in an extended body, that's what we mean by a system of particles, why this special point called the center of mass is so important. And then we talked about how you determine the location of the center of mass. And it really boiled down to for a system of particles. But we also talked about how to find the center of mass when the object is an extended body made up of relatively simple shapes, each with mass uniformly distributed throughout it. In that case, you could take the extended body and you could take each of those shapes and put all its mass, collapse all its mass down into a point at its geometric center, and then use the formula for the center of mass of a system of particles. Okay, so if the center of mass is important, probably the most important point on an extended body, then we want to know how that center of mass is going to move. What determines how the center of mass will move? How can we predict the future motion of the center of mass of an extended body? I'm going to state for you the answer without any detailed proof. If you want a little bit more justification, you can read our book, Chapter 9, Section 2. But I'm going to tell you the upshot right now. There is a form of Newton's second law specifically for the center of mass point. And that's what we would use to determine how the center of mass will move. Okay? So I'm now going to state Newton's second law for the motion of the center of mass. And it looks just like Newton's second law with a few important subtle distinctions that we have to be aware of. When we talked about a single particle, we wrote A vector equals F net vector over m. Now here was what we write. The acceleration specifically of this point called the center of mass, ACOM vector, is given by, okay, well, there's a force on the right and a mass on the right. Let's see what those are. Upstairs, notice what I've written. F arrow subscript NET, comma, EXT, because that subscript is very important. The NET means net. You have to have the total force, but it's got to be what are called external forces on the system. Forces on this system of particles from the outside, not from internal forces from one particle inside the system pushing or pulling on another particle inside the system, but only external forces acting on the system. And you add up the total of all those external forces, vector addition, and you get F net external. That's what goes in the numerator on the right-hand side. And what goes in the denominator on the right-hand side? The total mass of the system. The total mass of all the particles that make it up. So that's how we will determine the motion, specifically the acceleration, of the center of mass of a system. We will add up the net external force and divide by the total mass. But it's a vector equation, so really this has to be written out separately by x and y and maybe even z components. Now, let me give you a tip for one of the ways that this formula, I can immediately tell you one of the ways it's useful. Okay? So here comes our first useful consequence of this Newton's second law for the center of mass. Suppose you have a situation where the net external force on your system is 0. That might be because there are no external forces whatsoever, That would probably be more likely if the system were out in deep space, far away from anything. Or because there are multiple external forces, but the net of them, the vector sum of them, is zero. The external forces balance each other out. That's more likely to happen here on Earth, but it can happen. So suppose that is what happens. We have a net external force equal to zero on our system. Then Newton's second law for the motion of the COM says you put a zero in the numerator on the right-hand side. Whereas, of course, the denominator on the right-hand side, the m, that's not zero. So I've got a zero on the right-hand side. Therefore, the acceleration of the center of mass must also be zero to maintain the equality. So if the net external force on a system equals zero, then the acceleration of the center of mass must equal zero. The center of mass can't accelerate. Now, from the very definition of acceleration, we know that the acceleration of the center of mass, vector, is related to the velocity of the center of mass vector by a derivative. That is to say, the time derivative of the velocity of the center of mass must equal the acceleration of the center of mass. That's just applying a Chapter 2 idea to this special point called the center of mass. So if I have a situation where from Newton I have learned that the center of mass acceleration equals zero, then it must be true that the derivative of the velocity of the center of mass equals zero. But if the derivative of a quantity equals zero, then the quantity must be constant. Okay? Just highlight it. So if ACOM equals zero, then VCOM must be constant. So if the acceleration of the center of mass is zero, the center of mass can move, that's its velocity, but that velocity of the center of mass cannot change. And that can be a very helpful idea. It's very basic to state. It can be very helpful in certain situations in predicting the future motion of a complicated system. I'm going to do a Wiley Plus problem where we use this very idea. That'll be in the next video. Okay? Okay. So, in principle then, determining the motion of the center of mass boils down to determining the acceleration of the center of mass. Presumably from that you could then get the velocity and the displacement. And we get the acceleration of the center of mass by applying a form of Newton's second law, specialized form of Newton's second law. So let's go right to some practice with motion of the center of mass and some simple calculations that I want us to do together. Now, before I do that, let me motivate a little bit more with a couple of videos how understanding the motion, or lack thereof, of the center of mass can be helpful. Okay? All right, so let me start with, okay, I'm going to show you a video. Got to get to the right place, okay? And what this video shows is a kind of an inclined plane or ramp, with the low end on the left going slightly higher on the right. Right? It does go up a little bit, just looking at it on a tabletop. And then, let me start the video a little bit. There we go. And what we're going to take is a double cone. Sorry, the video is choppy. Okay, a double cone with the two bases glued together and an axle going right down the center. That axle is a line of symmetry. Right? The mass distribution of the double cone is symmetric about that axle going through the middle. Therefore, we know the center of mass of this combined cone, double cone, must be somewhere along that axle, presumably in the geometric, roughly in the geometric center. I'm going to place the double cone at the low end of the inclined plane and let go. What is it going to do? Generally speaking, if I just place something at the base of an incline and let go, nothing happens. Whoa. What? It rolled up the ramp, up the incline. Since when do things, if you just let go of them at the base of an incline, roll up? Do you see why it did what it did? Understanding the motion of the center of mass can be helpful here. Because remember, the center of mass is roughly in the middle of that axle. And if you look carefully in the video at the beginning, when I release it, and look at where the axle is above the tabletop, and then after it rolls, and look where the axle is above the tabletop, it turns out that the axle is actually lower when it's at the end of its motion. The center of mass has actually gotten closer to the ground. So what we've done is we've reduced the gravitational potential energy, mgy, because there you need YCOM, and YCOM is less. So what we've done is we've converted gravitational potential energy into kinetic energy by letting the center of mass get lower. Okay, so there is a video where, if you understand motion of the center of mass, I hope that played well, then that makes sense. Now let me show you another video. This has a piece of wood with a hole in it, and the ends of the wood are cut at an angle so that the piece itself will not stand upright on its own on the tabletop. There's the hole, the cut end at an angle. If I just let go, it doesn't stand up on its own. Now we take a wine bottle with wine in it, corked wine bottle. All right, what are we going to do? Well, seems magical, doesn't it? That whole system now of wine bottle plus piece of wood is able to stand there at rest, balanced. How can we understand that? Well, there's quite a bit to talk about there, some of which we haven't talked about specifically, but the basic idea is that the center of mass of the wood part alone is somewhere roughly in the middle of the wood, and the center of mass of the wine bottle alone is probably a little bit more towards the left, behind the label, where more of the mass is. But the center of mass of the two things together, the wood and the wine bottle, must lie vertically aligned with that base on the piece of wood that's supported on the tabletop. The center of mass of the combined objects, wine bottle plus wood, must be vertically aligned with the area of support of the base on the tabletop, and then the system can remain without falling over. Okay? So understanding center of mass helps us understand a little bit about why that whole thing doesn't just fall over. Okay, so now let's do some practice with the motion of the center of mass. Bring that up just a little bit more. And we're going to go back to an object that I showed you a video for back in chapter 4 when we first started studying projectile motion. It was called the shooter dropper. And the apparatus took two objects, and it just dropped one and let it fall vertically with an initial velocity equal to 0. And it shot the other one with an initial velocity that's purely horizontal. But then they fall the same height to the tabletop. And you discover that although they have different horizontal motions, one of them has no horizontal motion at all, just falls vertically down. The other one has both horizontal and vertical motion, so they have different horizontal motions, but they have the same vertical motion, and that they actually hit the ground at the same time. That was meant to demonstrate that the horizontal and the vertical motions are independent of each other. But now I want to look at how the center of mass of a shooter dropper will move as the shooter and the dropper move. So now I'm going to show you the shooter dropper in a Wiley Plus animation. And that consists of two particles. Particle 1 will be the dropped one. Dropped from rest at a height of 1 meter above the ground. I'll show you the animation in a minute. At the same instant that particle 1 is dropped, particle 2 is given an initial horizontal velocity of 0.10 meters per second in the same location. We call that a shooter dropper. Okay? All right, so let me show you the Wiley Plus animation. So you can see a y-axis and an x-axis. They both happen to be scaled in centimeters. The shooter and the dropper are actually starting at the same point. You can think of one as right behind the other. I put them at x equals 10, y equals 100 to start with. And right now they have equal masses because that slider you see there labeled m1 divided by m2 is equal to 1. And the red arrow you see represents the velocity of the center of mass. The blue arrow is the position vector of the center of mass. Points out from the origin to where the center of mass is. So I'm going to first just run the animation so that you can see the dropper fall and the shooter go out horizontally along projectile motion, and that you can see them hit the ground at the same time. There they go. And they hit the ground at the same time. Particle 1, the dropper, straight down. Particle 2, the shooter, starts out going horizontally, but of course because of gravity follows a parabolic trajectory and curves down and also hits the ground, but they hit the ground at the same time. I also show the motion of the center of mass with the dashed curve. That's the trajectory of the center of mass. Notice that for most of the time there is no actual mass where the center of mass point is. But you can see the center of mass moves, and it's pretty much right in between, midpoint between the two particles, because the masses are equal. And it also lands on the ground at the same time as the particles themselves. And the velocity of the center of mass, the red arrow, changes as the whole system falls, right? The red arrow is the velocity of the center of mass. Okay, now here come a series of questions. Let's go back to our notes and look at the first question. And we're going to work out the answers together here. Question number 1. What is the x component of the center of mass velocity? A lot of words. Here it is. VCOM x component at t equals 0. If the two particles have equal masses, which the animation shows. Okay? All right, let me move this up a little bit. And so I have some room. And let me start writing some ideas down here to answer number 1. Let's start with the expression for finding just the x-coordinate of the center of mass. Now that we learned in the previous video lecture. It's a two-particle system. I have two particles, particle 1, particle 2, the dropper and the shooter. So the formula says to do the sum, index I going from 1 to n is 2, take the mass of each particle over the total mass times the x-coordinate of each particle. That's easy to write out if you really only have two particles. It means take m1 times x1 plus m2 times x2 and divide it by the total mass, big M, where that just means big M, m1 plus m2. Okay? All right, that's how you would find XCOM. And we could figure that out if we were asked to. But what it asks us to do is to find the x component of the velocity of the center of mass. How do we do that? We take this very expression I just wrote down for XCOM, and we use a kinematic idea from chapter 2, that the velocity is the derivative of the position. So the x component of the velocity is the derivative of the x position. So VCOM x component is the derivative of the x-coordinate of the center of mass, xcom, with respect to time. dxcom dt. And this right here is the formula for xcom. That's what I have to take the derivative of with respect to time, using what I know about physics and about calculus. Well, I think of the factors of m1 and m2 and m total as either multiplicative or divided constants. Those just get carried along for the ride when you do derivatives. They don't go to zero. They get carried along for the ride. So the m1 and the m2 and the big M are going to stay exactly where you see them. But the derivative part is going to act on the x1 and the x2. dx1 over dt will be there, and dx2 over dt will be there. But from chapter 2, the derivative of x with respect to time is the x velocity. So what I'm going to be left with is, upstairs, m1 times the derivative of x1 with respect to t is the velocity of particle 1, x component. So I've replaced x1 with v1, x component, plus m2, and I replace x2 with v2, x component, all divided by capital N. See, it's actually a very simple little progression from xcom to vcom(x). You just replace x1 and x2 with v1x and v2x, but it's only x components here. Okay? And I'm going to plug in numbers now for v1x and v2x at the instant t equals 0, right? Because that's when it asks for vcom(x). Here's something else I'm going to do while I'm at it. Since particle 1 and particle 2, the dropper and the shooter, have the same mass, I don't need to write m1 and m2. I'll just write m, because it's the same. All right, so here we go. For vcomx at time 0, m times, okay, what is v1x at time 0? Particle 1, it's x velocity at time 0. Particle 1, remember, is the dropped one. It's dropped, so it has no x velocity, correct? So v1x at this moment is 0. So you put a 0 there. Plus m again for the shooter. What is v2x? Well, you can't see it. The words are scrolled up off the top, but we are told that particle 2 is given an initial horizontal velocity of 0.1 meters per second. Horizontal means x. So they're telling me this very number I need, v2x at time 0. It's 0.1 meters per second. Okay? And that's divided by the total mass. Well, I think that would be 2m. Now, this first term is gone here. That's 0. And I have an m upstairs and an m downstairs, so those cancel. So what is left? What is vcom(x) component at time 0? In the numerator, I have a 0.1 meter per second. And in the denominator, I have a 2. So 0.1 meter per second divided by 2 is 0.05 meters per second. And that was represented in the animation by a horizontal red arrow. So let me go back to the animation. Let me reset it. A second, okay? There you see that horizontal red arrow. That represents the velocity of the center of mass. It has an x component. Okay? So we have done part 1, just practicing calculating something, some information about the motion of the center of mass. Let's go on to part 2. How does the value of VCOMx change with time during the motion up until the moment the particles hit the ground? Right? So, what can we say about how VCOMx changes with time? I'd like you to think about that a minute, make a prediction for yourself, pause the video, and then when you're ready, start it up again. Okay, here you just need to think about the physics a bit. We want to know how VCOMx changes with time as the dropper drops and the shooter projectile undergoes projectile motion. Well, the dropper just drops vertically. It never has an x velocity, does it? Ever. So, up in this formula, in part 1, where I calculated VCOMx, it turns out that V1x is always equal to 0. Always. What about V2x? Well, now that one has an x velocity, doesn't it? Particle 2 is the shot one, undergoes projectile motion. But remember what you learned about projectile motion in chapter 4. What can you say about the x velocity of a projectile? Remember, it's constant? Because the gravitational force is vertical. There is no horizontal force to change the x velocity. So V2x, it's not 0, but it is constant. At what value? At 0.1 meter per second. So this calculation I did for VCOMx at time 0 is valid at any time up until they land. So VCOMx is constant. Okay? You can actually see that if I go back to the animation. And I'm going to do that. And when we run it, again, I want you to look at the red arrow representing VCOM, and I want you to envision its x component, its horizontal component, and see if you can see that that isn't changing. All right, let's run this again. Give it a second here. See if it will run. Okay, for some reason, it's not cooperating. Wiley has gone on strike, and I don't know why. Okay, so I can't show it to you, unfortunately. I think what I will do is I will pause. Okay, I'm back. Hopefully the animation is going to run now. And I'm going to have you watch the red arrow, which is the velocity of the center of mass. As you can see, it definitely is changing in magnitude and direction, but the horizontal component of it is not changing. The horizontal component of VCOM is always that, right there. Okay? It must be the vertical component of VCOM that changes. Of course, that's because of gravity. But the horizontal component of VCOM is always that right there. Okay. All right. Now let's go on to question 3. I'll read it to you for the shooter dropper. What is the y component of the velocity of the center of mass, VCOMy, at t equals 0, if the particles have equal masses? So now we need to calculate VCOM y component. Now we've got to deal with components when we have vectors, right? Got to just be dealing with components. Now the good news here is I can just write down the formula for VCOMy based on the formula for VCOMx. All I have to write is this: VCOMy equals m1 times v1 y component plus m2 times v2 y component over total mass, total m. Right? It's all y components for the velocities now. And then I plug in the values for v1y and v2y at time 0. So here we go. Remember, I'm also going to change m1 and m2 just to m. And big M will be 2m. So we'll have m times v1y. Particle 1 is the dropper. It starts from rest. Its initial y velocity is 0. So 0. Now, plus particle 2, m times, well, now particle 2 had an initial velocity. Aha, but that initial velocity was purely horizontal. The initial velocity of particle 2 has no vertical component at all. So v2y component is 0. Got to think about it along the lines of components. Over 2m. Well, but that's a 0 in the numerator, so the answer is 0. Now this is at t equals 0. But of course the animation shows the red arrow representing VCOM, and at t equals 0, that red arrow is purely horizontal. All right, that wasn't too hard. Now let's go to question 4. What is VCOMy, the y component of the center of mass velocity, just before both particles reach the ground, assuming the particles have equal mass? So we do VCOM calculation again, and I'm going to plug in to this formula right here. I just have to plug in v1y and v2y when the particles just get to the ground. So I need the values for v1y and v2y as they get to the ground. Those are chapter 2 problem for the dropper and a chapter 4 problem for the shooter. Kinematics problems that we've done already. Let's say that height is h. We know it's 1 meter or 100 centimeters, but let's just call it h. Then we've done enough kinematics, you should be able to convince yourself that the following is true. Just use the constant acceleration equations. From kinematics, particle 1's y velocity and particle 2's y velocity will both be the same. It'll be negative square root of 2gh. Negative, right? Downward. Square root of 2gh, where h is the initial height. And they're the same. Okay? The particles are undergoing the same vertical motion. So we plug that expression in for v1y and v2y. Let's see what we get then for VCOM y component, just as they reach the ground. For the first particle, m times negative square root of 2gh, there's for particle 1, plus now particle 2, m times negative square root of 2gh, all divided by 2m. This is crying out to be simplified. Look at the numerator. It's the same thing added to itself. So that's 2 times the thing, right? So that's negative 2m square root of 2gh. That's the numerator, and the denominator is 2m. Well, look at that. There's a 2m in the numerator and a 2m in the denominator. So the final answer for VCOM y component, just as the 2 particles reach the ground, is negative square root of 2gh. The same as what the individual particles' velocities were. That's because the particles have equal mass. Now, you can plug in the numbers if you want, and we could do that. VCOM y component. Remember, h is 1 meter. Got to convert it to meters. G, of course, is 9.8. Multiply those out, multiply by 2, take square root, put in a negative sign. You get negative 4.43 meter per second. Okay, that's what the y velocity of the center of mass is, just as they reach the ground. Okay, right there. Negative and 4.43 meters per second. What's the x velocity of the center of mass when they reach the ground? 0.05 meters per second. So considerably smaller than VCOM-y. Okay, now, let's look one more time at the animation. And run it. Hopefully it will run. There we go. And it does look like, look at the VCOM vector here at the end, just as they reach the ground. It sure does look like the y component is considerably larger than the x component. That's what I want you to see from that. Okay? Now I want to do a little more by way of calculation, although it's not asked. I want to go ahead and kind of do some bonus questions, some extra. And to do that, let me go back to my notes here. And let me get myself a little bit of room. Let me erase so I have some space. I'll leave the formula for VCOM-y visible. Okay? And here's a little bonus question. What is the acceleration of the center of mass y component for this shooter dropper? How might we figure that out? I'm going to do it two ways, using kinematics and then dynamics. I'll explain. First, from kinematics. From kinematics, acceleration is derivative of velocity. So ACOM, y component, is what you would get if you take VCOM, y component, and you take the time derivative, d by dt, of VCOM, y component. Okay? So then I just take the formula you see right up above for VCOM-y component, and I take the time derivative of both sides. And all that happens is where the V1y and the V2y are, you get A1y and A2y. It's that simple. So you have M1 times A1y component plus M2 times A2y component over total M. And now I'm going to substitute in what I know about A1y and A2y from the motion we've already studied, free fall and projectile motion. We know what the y velocity is for particles in free fall and projectile motion. The y velocity for both of them is negative little g. Right? It's just negative little g. So you plug that in. Now remember the masses are equal, so I'm just going to replace M1 and M2 with a little m. And what I'm going to have in the numerator is negative 2 little mg. And what I'm going to have in the denominator is the total mass, 2 little m. And again, the two m's cancel. And I'm left with the fact that ACOM-y component is just negative g. Constant, right? The acceleration of the center of mass of this shooter dropper is constant, because the vertical motion for both is determined solely by gravity, which is a constant force. Okay, that probably seems reasonable. Now let me get the same answer for ACOM-y by using dynamics. Dynamics, remember, is why does something move the way it does? And our main tool in dynamics is Newton's second law. So I use Newton's second law for the motion of the center of mass, that formula that I just showed you at the beginning of the video. And I'm going to focus on y components. Newton tells me that the acceleration of the center of mass, y component, must equal the net external force y component over the total mass. Okay, that's dynamics. That's telling me why I have a certain acceleration, because I have a force. And so what I have to put in on the left-hand side, the right-hand side, is the net external y force. The system is the shooter and the dropper. So Earth is external. So the gravitational force is external. And it's in the negative y direction. So for particle 1, the external y force is negative m1g, or negative mg. Plus, now for particle 2, also negative mg. And the denominator, total m, 2m. So this is still negative 2mg over 2m. The 2m's cancel, and I get negative g. Okay? So whether I approach it from what I know about kinematics or what I know about dynamics, I conclude that the acceleration of the center of mass y component for this object, this system, is negative g. Okay? All right, the last thing I'll show you on this animation is how, if I change the mass ratio of the two things, the dropper and the shooter, the center of mass does get affected. Because remember, the center of mass is biased towards where most of the mass is. So I'll just leave the time slider where it is, but I'll change the mass slider. And if I slide the mass slider m1 over m2 to the small end, I'm making m1 very small and m2 very big. So most of the mass is at 2. 2 is the shooter. So notice the center of mass moves over closer to the shooter. If I go in the other extreme and make m1 over m2 big, 10, then particle 1 has most of the mass, and the center of mass is closer to it. All right? And we can even see the center of mass move, but the center of mass will be closer to where the most mass is. Okay, now let's go back to our notes, and I have one more idea to introduce in this video. Now I'm moving on to chapter 9, section 3, and we're going to introduce a brand new quantity that turns out to be actually very important in physics, and its name is linear momentum. And let me just start with its definition for a particle. All right, with outright definition, one of those things that we just have to have in our head. The linear momentum of a particle, this is for a particle. The particle has mass m and velocity v. Notice velocity vector v with components. Here's the definition. First of all, the symbol, lowercase p. Note the arrow on top. It is defined to be the mass times the velocity. Again, note the arrow. That's a simple definition. That's the definition of the linear momentum of a particle. Take the particle's mass and multiply it by the particle's velocity. Now remember, the velocity in principle can have 3 components. So what this really means, if I write it out in unit vector notation, is m times, parentheses, the x velocity times I hat, plus the y velocity times j hat, plus the z velocity times k hat. The SI unit of linear momentum is the unit of mass, kilogram, times the unit of velocity, meter per second. Kilogram times meter over second. And note that unit does not have its own name. It's just kilogram meter per second. But yes, linear momentum is a vector. Components. Okay? All right. Now, why introduce some? Don't we have enough quantities? Why introduce yet another? Turns out linear momentum is more fundamental than, say, acceleration. And in fact, Newton's second law, as we have been using it now for quite a few weeks, that's not the way Newton actually wrote it. And I'm not talking about the fact that he actually originally wrote his book in Latin. But he didn't even express the idea that we call Newton's second law the way we have been doing it. I'm now ready to tell you how he expressed what we now call Newton's second law. Okay, so that's another key idea. I just describe it as an alternative version of Newton's second law, but it's really the way Newton wrote it. Okay, how Newton expressed it. Okay, once translated into modern language. Here we go. Start with Newton's second law in a form we're more familiar with. F net equals m times a. Vector formula, look at the arrows. Now, let's put in the definition of a. Derivative of velocity with respect to time. That's true. Next, because we're talking about a particle, the assumption is that the mass, unchanging. Particle can be moving all around, but its mass is not changing. And since the m is multiplicative out front of the dv dt, you can take the m inside the time derivative, right? For the simple reason that, let's come up here. If I ask you to take the time derivative of 5t, you can think of it this way. You can bring the 5 out front, and you can take the time derivative of just what's left. This happens to be a t. Or maybe if I wrote it as 5t squared, then you can still take the 5 out front, and you've got to take the time derivative of what's left, t squared. So the m, since it's a multiplicative constant, can be taken inside the derivative. And now what you're taking the time derivative of is the combination m times v. But that's our definition of our new quantity, linear momentum, p arrow. So F net actually must equal dp dt. Or to say it in words, the net force on a particle equals the rate of change of the particle's linear momentum. That's what Newton expressed. If there's a net force on a particle, the particle's linear momentum will change. And in fact, that net force will equal the rate at which that linear momentum will change. That's what Newton expressed. Now, this is a vector formula, F net equals dp dt. So you really have to operate by components. You have to write it for the x components. F net x equals dpx dt. And then for the y components, F net y equals dpy dt. And I want to show you how you have to deal with components in another short animation with a little calculation that goes with it. Okay? So I want to show you an animation, the purpose of which is to emphasize that a net force changes the linear momentum of a particle. So now let me go back to Wiley Plus and click on my second tab. Good, okay? Now you're seeing another picture. You're looking down from above on a horizontal XY system, okay? And initially a particle is moving in the plus x direction. So it has a linear momentum, p arrow, that is purely in the x direction. And that's what that kind of gold or orange arrow represents. The particle is the blue disk at the origin at time 0. So that red arrow, that gold or orange arrow you see represents the linear momentum initially. Okay? If you like, p initial. I'm going to run the animation. It's going to run for a little more than 6 seconds. And for the first 3 seconds, nothing much is going to change. But for the time interval between 3 and 6 seconds, there'll be a constant force of 0.5 newtons acting in the positive y direction. That will be represented by a blue arrow. Okay, I'm going to run it. I want you to see the blue arrow up here. That means the y force is acting on the particle. And I want you to look at what happens to the particle's linear momentum vector because of the force. First 3 seconds, nothing. Then at 3, there's the force. Look, the momentum vector is changing. Now the force goes away, and the linear momentum vector doesn't change anymore. All right? So initially, no force, constant momentum. Then the force kicks in at t equals 3, and the momentum vector changes. And then after t equals 6, the force is gone. And then the momentum vector cannot change anymore. All right, here's what I want us to calculate. I'm going to give you some numbers so that we can do it. I want us to calculate the final linear momentum of this particle right here at the end of the animation. What is the final linear momentum? All right. Go back to my notes. And here's what I'm going to tell it, information I'm going to tell you. The mass of that particle, 0.5 kilogram. The initial velocity, v initial, is 1.5 meters per second, I hat. Right? Initially, it's moving purely in the x direction. That applied force, F, that you saw, represented by the blue arrow, is 0.5 newtons, j hat, for the time interval, t, between 3 seconds and 6 seconds. I want us to calculate the final linear momentum. Okay? P final arrow. And of course, I want the answer in unit vector notation. Well, that means I have to find P final x component and multiply that by I hat, and P final y component and multiply that by j hat. And how do I find P final x and P final y? The new version of Newton's second law. F net x equals dpx dt. F net x equals the rate of change of p sub x. But you saw the animation. What is F net x? Was there any x force? No, the force was only in the y direction. So F net x is equal to 0. So dpx dt equals 0. But if the derivative of something equals 0, then what do you know about the something? In this case, p sub x. It's constant, right? So the p sub x value is equal to a constant equal to whatever it was initially, p initial x. Yes? So that will just be the mass times the initial x velocity. All right, let's plug in the numbers because we know that. So px is constant. It's equal to the mass, 0.5 kilograms, times the initial x velocity, 1.5 meters per second, and you get 0.75 kilogram times meter per second. That's px. It's equal to p initial x, and it's equal to p final x. Px is constant. That was easy, because there was no x force. Now let's get the y component of the final momentum. How will we do that? Use the y component of this new version of Newton's second law. F net y equals dpy dt. Now, at least for that 3-second interval, F net y, not 0. When F net y is 0, then py is constant. But when F net y isn't 0, py changes. Okay, now what I'm going to do with this formula is something that physicists do all the time. I want the change in p sub y, because of that 3-second time interval when F net y was acting. So what I'm technically going to do is integrate both sides, but I'm going to do it in a way that to a physicist seems the most straightforward. I'm going to multiply both sides of that formula by a dt and treat the right-hand side like a fraction. So I get F net y times dt. And if I multiply the right-hand side by dt, the dt downstairs cancels the dt upstairs, and I'm just left with a dpy. So I just multiplied both sides here and here by dt, and then cancel, cancel. Okay? Now remember that for that 3 seconds, while the, pardon me just a second here, for that 3 seconds that the force is acting, it is constant. And so I integrate both sides of that. And on this side, I just get the finite change in the y momentum. And the net y force is constant. So on the other side, I get F net y times the finite change in time. That's what you get for that 3 seconds. So that would be at the end of that 3 seconds when the force was acting. That's how much the y momentum is going to change. Note, change because of that y force. Let's see how big that change in the y momentum is. Remember, F net y is 0.5 newtons. And the time interval for delta t is 3 seconds. So, of course, that's 1.5 kilogram meter per second. That's the change in the y momentum. Okay, but the final y momentum will be equal to whatever the initial y momentum was, plus how much the y momentum has changed. It's kind of what change means, right? If you've got a certain amount of change in something, you take the initial value plus the change, and you get the final value. But what was the initial y momentum? The initial y momentum, it's all about vectors again. The initial y momentum was 0 because the initial y velocity was 0. So the final y momentum comes totally from whatever that change in the y momentum was, which is 1.5 kilogram meter per second. So now I know P final x, 0.75 kilogram meter per second, and P final y, 1.5 kilogram meter per second. So P final arrow is P final x, 0.75 kilogram meter per second times I hat plus P final y, 1.5 kilogram meter per second j hat. And that is the final momentum of our particle, being very careful to deal with the fact that it's a vector and you have to work separately with the x and y components, and the fact that the x momentum did not change because there was never any x force, but the y momentum did change because there was a y force. Okay? So momentum is a vector, and the rate of change of that vector momentum is given by the net force. And that's what Newton actually said for what we now call his second law. Okay, so the next video will be a class video where we're going to apply this concept of determining the motion of the center of mass. That's all for now.